History is defined by moments, where everything changes in an instant. Welcome to History's Incident Files. Hit subscribe and let's explore the past.
Welcome to History Incident Files. I am your digital host, Stephen Franklin. Today we're going to be covering the 1940 Tacoma Narrows Bridge disaster. On November 7th, 1940, Washington State's brand new bridge collapsed in 40-mile winds. But the real story isn't just the collapse, it's the bizarre engineering flaw that made it happen. Here we are in downtown Tacoma, 1940. The city is buzzing about their brand new engineering marvel. But in just a few hours, history will change forever. In 1940, this wooden ferry was the primary link. It carried people daily between Tacoma and the peninsula, a quiet witness to the growth of the Puget Sound region. For decades, the only way across was by ferry, slow and at the mercy of the tides. So when Washington State proposed a bridge, the public didn't just want it, they needed it. The job went to engineer Leon Moissafe, one of the most respected suspension bridge designers in the country. His pitch? Make it elegant, make it cheap, make it thin. Engineers used solid 8-foot steel plate girders along the deck instead of open trusses. That solid steel wall acted like a giant sail, trapping the wind instead of letting it pass through. Where the Golden Gate Bridge used a deep, rigid truss to stay stiff, Moissafe went with a shallow, solid girder, just 8 feet deep, for a deck 39 feet wide. A ratio of nearly 1 to 350 between depth and length. Compare that to the Golden Gate's roughly 1 to 170, half as stiff for a span nearly as long. From opening day, motorists noticed the road undulating up and down like a roller coaster. Drivers traveled miles just for the thrill of driving. Galloping Gertie. Construction began in November 1938. It took under 2 years and cost about $6.4 million. But almost immediately, something was wrong. Even in light wind, the deck began to undulate, rolling in gentle waves, up and down, along its length. Construction crews started calling it Galloping Gertie. Some got seasick just walking across. On the morning of November 7th, 40-mile-per-hour winds hit Puget Sound. But this time, the motion didn't just ripple up and down, it twisted. Moissafe's solid girder sides acted like a wing or a sail. Wind couldn't pass through it the way it would through an open truss. Instead, wind hit the deck and peeled off in swirling vortices, alternating above and below. Each swirl gave the deck a tiny push, first up, then down. Normally, that's harmless noise. By 7:30 a.m. on November 7th, gale-force winds reached 42 miles per hour. The vertical suspender cables hummed loudly as the wind pressure surged. Engineers call this aerodynamic flutter, a feedback loop where the structure's own motion starts feeding the forces that move it. And Gertie's design, thin, light, and flexible, was almost a textbook setup for it. State officials brought in experts, including engineer Farquharson from the University of Washington, to study the motion. Stiffening cables and hydraulic buffers were installed to try to dampen the sway. It helped, a little. At 10 a.m., the deck began violently twisting 45 degrees side to side. One sidewalk rose 28 feet above the other. November 7th, 1940. Winds gusting at 35 to 42 miles per hour. Strong, but nothing the bridge hadn't handled before. Around 10 a.m., news editor Leonard Coatsworth started driving across, heading home. His daughter's Cocker Spaniel, Tubby, rode in the back seat. Around 10 a.m., 40-mile-an-hour wind gusts hit the deck. The roadway began to twist violently, pitching 45 degrees into the air, then whipping back in the opposite direction. The bridge deck recoiled into a violent counter-twist, placing extreme tension on the main suspension cables. Coatsworth slammed on his brakes, abandoned his car, and moved carefully along the walkway to reach the safety of the main tower. His daughter's dog, Tubby, was still trapped in back of his car. Professor Farquharson, who was on site taking motion pictures, ran onto the twisting bridge in a desperate attempt to save the dog. Farquharson reached through the open window, but the terrified dog bit him. Bleeding and exhausted, Farquharson had no choice but to retreat to safety. By 11 a.m., the structural cable bands reached their breaking point. At 11:02 a.m., the main cable snapped, and the entire center span tore free. At 11:02, a key steel cable band snapped under severe tension. At 11:02, the center of the bridge gave way, plunging into the water below. And the middle section was in the Puget Sound. Tons of steel and concrete smashed into the water below, sending spray high into the air. In minutes, the pride of Washington engineering was reduced to twisted wreckage drifting in the Sound. The disaster shocked the world. Engineers immediately built scale models inside wind tunnels to study what went wrong, discovering a phenomenon called aeroelastic fluttering. Headlines shocked the nation. The world's third longest suspension bridge had collapsed in 40-mile-per-hour winds. Stunned crowds gathered along the shore, gazing out at the empty gap where the bridge had stood just hours before. Investigators discovered that solid steel side girders trapped the wind, creating aeroelastic fluttering that destroyed the bridge. The disaster permanently changed bridge design worldwide, birthing the field of bridge aerodynamics. Lessons learned from Galloping Gertie changed suspension bridge engineering forever. 10 years later, a replacement bridge opened designed with open steel trusses that let winds blow safely through. 10 years later, a new Tacoma Narrows Bridge opened, built with open steel trusses that let the wind blow safely through. Thank you for joining us for this historic disaster. Hit that subscribe button for more history incident files, and we'll see you on the next incident.